Hello, everyone, and welcome to this talk. Today's talk is about learning context variables in contextual reinforcement learning. I will start with an intro to reinforcement learning, and then I will talk a little bit about contextual reinforcement learning and the related methods. Next, we will have a look at the generative view on contextual reinforcement learning, and we will discuss how we can learn context variables in this context. And finally, we will discuss how we can learn causal factors of the context variable that helps us to better generalize. All right. So in reinforcement learning, if you're familiar with, usually an agent interacts with an environment and changes the environment by executing actions and by receiving a reward from the environment. And this has been a classical formulation, and we can define this via this diagram, and we can define this via a Markov decision process, MDP, or a partially observable version of it. Reinforcement learning can be used for tackling different kinds of problems. For example, for sim to real, we can simulate an environment and train a policy, and then push this policy to a robot that interacts with the real world instead of the simulation. Or we could use it in, for example, a multi-agent setting where different agents have to kind of work together to solve a task. And as another example, we could use reinforcement learning for autonomous systems, for example, for self-driving cars, where there are some sensory inputs to the system or the agent, in this case being the self-driving car, and then the agent or the car has to kind of decide what actions to take. And in all of these cases, actually, when the environment changes, there could be some aspects of the environment that change based on some factors, which we call in this case context. For example, we can think of lighting as a context. If we have a self-driving car, if the lighting changes during the day or during the night, the observations, if the system is using, for example, video input, then the distribution of the input changes. While it could be exactly the same location, it looks different. So we can think of this as a new context, which our model has to be able to generalize to. We could also think of it as the location that defines the context. If, again, we are talking about self-driving cars and we are trying to pick the correct series of actions in a cross-section, depending on where this cross-section is it in a crowded part of the city, is it in a highway, our policy should actually behave differently, depending on the context. So in contextual reinforcement learning, we are actually focused on exactly this problem, and the issue often is when the agent is interacting with the environment during training, when the context in the environment changes, the agent might fail to generalize because the change in the context might affect the distribution of the observations, and further, it might affect the distribution of the reward where the agent is actually receiving the reward. So it might affect the credit assignment and related topics. Also, because of these changes, the optimal policy might be affected by the context. So there has been a body of work in this direction. For example, a paper defined contextual multi-decision processes or contextual MDPs, where the context space consists of k possible contexts, and within each episode, actually the environment chooses a certain context, which is fixed during each episode. And based on this definition, then this paper provides a solution that uses some clustering on the observation and the trajectories into k clusters, and then kind of uses a classifier to classify what the current context is, and then tries to identify the context and exploit that the current context for the policy. However, this method has been only tested on low-dimensional state spaces and a small unlimited number of contexts. And because it is using different kinds of algorithms such as clustering, the success of the method depends on the success of each of these modules. In another work, a contextual decision process has been defined as a generalization of Markov decision processes or partial observable MDPs as well. And in this work, the observations or the history are those who form a context. Based on this definition, they propose an algorithm that tries to actually tackle the contextual reinforcement learning problem. Again, this problem is only designed for a constrained set of problems with a small Bellman factorization rank. And also, there are some additional constraints. For example, the Bellman rank needs to be known, and the class function has to have a certain cardinality and so on. Another work that tries to provide a solution for contextual reinforcement learning is the work that I said all you need, which actually uses mutual information between a current context and its observation as a learning signal, and the entropy of the policy between different contexts as a regularization. It uses this to to improve exploration and adapt to the change of the context. This work assumes that the context variable is known to the policy and uses actually this as a supervised signal. Another work known as variational optimal discovery algorithm, option discovery algorithm, uses a variational autoencoder and actually encodes the trajectories, encodes the context of the trajectories using the policy, and since it's an autoencoder, again, subsequently decodes the trajectory back to the initial context. And it uses a sequential variational autoencoder, and using a probabilistic decoder, it assigns high probability trajectories that are from a certain context. This method also assumes that the context variable is known and uses this information as a supervised signal to train the decoder. Another work that tries to design an agent that generalizes into new context is Darla, which uses an agent that has a pre-trained representation network that incorporates disentangled state representation into the model, which is trained using a beta VAE, and further uses this pre-trained model to actually learn the policy. This work actually does not take into account particularly a context variable, only disentangles the states, but they report the generalization onto new context is actually better than other approaches. And however, in case of limited data, this might actually have some limitations. For example, if the representation cannot generalize, it could become problematic for the policy generalization. Now I will talk about generative view and contextual reinforcement learning. And before that, I will explain what I mean by general generative process. So when we talk about a generative process, we mean that in our surrounding environment, there is a generative process in place such that everything that you observe in the world has been created in a two-step generative process. In the first step, a multivariate random variable z is sampled from a distribution P of z, where this variable z corresponds to some semantically meaningful factors and variations of the observation, for example, the shape of the objects, the number of objects, the color of objects, and so on. And in the first step of the generative process, we are actually observing those variables first. And after observing that, then the observation x is sampled from a conditional distribution of P of x given z. In this case, we assume that the observation space has a higher dimensionality compared to the semantic space, and also the data space can be explained with a substantially lower dimension compared to the observation space. So z has a much lower dimensionality than x. And the good thing is that if this can be hold true, then we can explain most of the information in x via z, which is actually very good. For example, in this case, if our z states that the color is green and the object is cat, after observing z by sampling from the environment and the conditional distribution of x given z, we can observe our high-dimensional sample from the data space or the state space X. Similarly, in contextual reinforcement learning, we can assume that the environment E of z, given the observation time step t and action at time step t, generates the next observation at time step t plus 1 as follows. And in this case, z actually is the variable that defines the context of the environment, and therefore we call this E of z. And by the change in z, the environment actually changes some aspects of the observation in time step t plus 1. And in the generative view, for contextual reinforcement learning, the observations are generated from the generative model in 3 steps. In the first step, a multivariate random variable C is sampled from the distribution P of C, where C corresponds to a context. In the second step, a multivariate random variable Z is sampled from a conditional distribution P of Z given C, where Z corresponds to the state of the environment that controls some aspects of the environment, for example, the statics. And further, in the third step, the next observation is generated from the environment. All right. Using this generative view, actually, we would like to know if knowing or having the context variable can be actually any useful in a contextual reinforcement learning setting. To test this hypothesis, we actually use a simple environment, which is based on the grid world. This environment is called contextual grid world. And in this world, the agent, the triangle, has to navigate the world, collect the goodies, avoid the obstacles, and arrive at the goal. And the difference between goodies and obstacles are the color, where the color of the goodie is encoded to the color of the agent itself. To evaluate the contextual abilities of agents, we always provide the agents with a context pair where all the colors are the same within a pair. However, goodie and obstacle has been flipped. By changing the color of the agent from one color to the other, we are changing the meaning of a color. For example, in the first context, in the context pair, yellow represents the goodie because the agent's color is yellow. In the second one, yellow becomes obstacle. And what we would like to know is that if we train an agent on a set of context pairs, will the agent be able to distinguish between the context in a pair? For example, will the agent notice that the policy should change depending on its own color or not? In addition to the reward, we would like to evaluate the discrimination ability of the agent in terms of the context. Therefore, we propose to use goodie obstacle discrimination, which is a simple measure as follows, that measures by the end of the episode how many obstacles have remained and how many goodies have remained. And what we would like to know, what we would like to have is actually to have 0 remaining goodies and maximum remaining obstacles, which in this case is 2. In addition, we would like to also evaluate if the agent reaches the goal in the end. Therefore, we just count how many times in the number of episodes that we ran the agent actually reached the goal. We evaluate 2 agents in this environment. One is non-contextual agent, which is simply just trained on the environment. One is a contextual agent that uses the ground truth variable, a one-hot vector that is given to the agent's policy in addition to the state representation. As can be seen, although in terms of the cumulative reward, the performance of the agent is similar, when we look at the goodie obstacle discrimination, we can observe that the contextual agent that had the ground truth context variable performed significantly better. And this tells us that actually by providing the correct context variable, we can actually change the behavior of the agent and make the policy better to the change of the context. Now, in that case, we provided the ground truth, but how can we learn the context variables ourselves? For that purpose, we propose a method called Context Adaptive Reinforcement Learning Agent, or CARLA in short, that actually uses a context network to learn a context variable, in which is then used along with the state representation in the policy, and what the policy is then trying to learn is a conditional policy that is conditioned in this context variable. So this context network is actually constructed from 2 parts. One is a feature disentanglement that is trained using unsupervised learning and is trying to learn a disentangled state representation from the input. And the other part is the part that is trained with reinforcement learning and tries to aggregate this information into a context variable. Having a closer look comparing the CARLA agent with some of the methods that discussed before, we can have a look at the graphical model. First, this is the graphical model of a VAE, where the gray circles show observed variables, and the white circles represent the latent variables. And we can see Darla and VAE have a very similar graphical model, while the variation option discovery algorithm has a different graphical model where the unobserved variable, the latent variable, is the trajectory, and the observed variable is the context. Our model has a slightly different graphical model where the representation or the latent representation of the state is different from the latent representation of the context that we are trying to estimate. And first, we estimate the disentangled representation Z, and based on that, we try to learn the context variable. Since we are relying on disentangled representation learning using variational autoencoders, we would like to investigate different kinds of VAEs and their effect on the performance of our model. In general, a variational autoencoder actually has an encoder-decoder architecture where the input is first encoded into a latent variable, and then is reparameterized to allow sampling, and then it's decoded back to the input. And it uses a combination of reconstruction and compression objectives. The compression is actually incorporating some prior. And the strength of this compression part of the loss often defines how much information can flow from the encoder to the decoder. And several work in the literature showed that by controlling the amount of information flow, you can actually control how the features are being disentangled. So we would like to investigate these, and in this work, we want to compare different VAE formulations with a focus on feature disentanglement. We look at some methods such as vanilla VAE and beta VAE that have a fixed weight for compression. We look at some methods such as anneal VAE that start with a high compression weight and gradually decrease the amount of compression to allow disentanglement to happen one factor at a time. And we also look at some methods such as Gecko that try to balance dynamically these two losses. To evaluate these different methods, we use disentanglement evaluation methods such as beta VAE score, which evaluates the quality of the disentanglement in the representation with respect to the ground truth factors that we have in our environment. Further, we would like to know how much information from the context are captured in our variable. Therefore, we do a simple context classification task using some simple models on the top of the encoded inputs. Here are some results from different VAEs that we use in the environment. And this table shows actually different beta VAE scores. And as can be seen, Gecko achieved the highest beta VAE score compared to the other methods. And we can also see that the reconstruction also looks better somehow compared to some other methods that we tested. And with respect to the context classification, we can also see using the vector extracted using the Gecko VAE, we achieved better context classification on both training and test. And these two results actually show us enough evidence to use this method as the disentanglement part of our algorithm. Now, assuming that we have this context variable learned, how can we incorporate this into policy? There are various ways of incorporating this context vector along with the state vector that we learned from the input. The simplest one is just to simply concatenate these two vectors and have a new vector fed to the policy. And another direction that has been investigated for conditioning mechanisms for example, multimodal learning or generative models is a film layer where it learns a scaling factor and a bias factor for different agents, and the conditioning vector actually controls the bias and the scaling of the state representation. You kind of doing a different thing, but it has been shown that it has been useful for some tasks. Okay. Now we would like to evaluate our agent compared to some available methods. For that, we use an actor-created vanilla policy gradient that actually uses entropy regularization, and we train our agent for 50 episodes, and then we use 45 context pair or 90 context during training. Here are some results. We can see the cumulative reward and the Goody upside discrimination, which was the main factor in here for us. We can observe that compared to the non-contextual agent, our Carla agent actually performs pretty well. And also compared to the Darla agent that uses disentanglement only without the addition of conditioning and the state representation, our agent performs much better. And even compared to the agent that uses the ground truth variable, we can observe that our agent has a better Goody obstacle discrimination ability. Comparing different VAEs, we took the best performing methods, Gecko and Beta, and we also compared the performance of both, and we see that the Gecko performs slightly better compared to the Beta VAE. And also we compare different conditioning mechanisms being using a film layer or concatenation layer, and it seems that concatenation works slightly better while being simpler. Since these two, the methods that we discussed as well as Carla, are somewhat offline methods because there is a pre-training using VAE stage, we here investigate the possibility of an online version of Carla where the disentangled part is being learned along with the policy itself using this algorithm that is described here. Comparing to the offline version of Carla, we can observe that actually the online version also learns quite well. And there is only a slight performance difference between them, which shows that our method can be used also as an online algorithm. Right. So after discussing how context variables can be used for contextual reinforcement learning and how important they are, I would like to discuss an aspect of causality and learning which factors are causal and which factors are non-causal in the context variables. Imagine the previous environment that we discussed before, and imagine that there is a causal agent that can distinguish which factors are causal in the context variable and which factors are non-causal. For example, the agent makes these decisions by discovering the relationship between the color of itself and the color of the goodie, and it knows that it should look at the color of itself and only look for that color and collect those. While a non-causal or a statistical agent actually just learns this joint occurrence of these colors and just switch the behavior based on this fixed observation and does not make the relation between the color itself and just memorizes kind of this joint occurrence of shape and color. If we train these two agents on a set of training contexts, considering given enough time, both of them should be able to solve the task on the training context, and both of them will be successful. However, if we provide the agent with a new context where it has not been seen before during training, only the causal agent will be able to solve this task. And a non-causal agent, obviously, because it has not seen these combinations before, will not be able to generalize. So actually, we would like to test this hypothesis in an experiment and see to what extent this is true, and also if we can design a mechanism that allows the agent to discover the relation between factors. And our goal is to actually build a mechanism into the agent that is able to discover the causal factors of the context variable. So for this purpose, for building this mechanism into the agent, first of all, we use disentangled representation learning as before to discover the factors of variation that exist in the environment, and further use these as a context variable, as we did in Carla, to learn conditional policies. However, in addition to what we did before, we would like to actually incorporate a mechanism that allows the agent to simulate different interventions and discover which interventions have a causal relationship and which don't. All right. For this purpose, we have designed a mechanism that uses a disentangled representation learning network to extract some disentangled factors and use them as keys. And from the state representation, actually, the agent learned a set of queries that come from the input. The difference between these two is that since we use a pre-trained and fixed model, the keys kind of represent different concepts because this disentanglement has been done in the environment and it's fixed. And given this set of keys and queries, we will then learn a similarity map, or better known as an attention map, that shows the kind of relationship between these two sets of queries and keys. And further, using this attention map, we copy the values from the input to the output, and we allow the agent to choose in each state which part of the input is more important and as is needed to be focused on. And by having this 60% representation, then the agent can kind of decide which factors have been useful for solving the task or not. We run an experiment. We train different agents on a set of 4 context pairs or 8 contexts for training, and then we evaluate them once on a 28 context pairs or 48 contexts with seen colors, meaning that these colors have been seen during training, but there are all new combinations of colors that have not been seen together. Also, we test these on a new 28 context pairs, which accounts for 56 new contexts with unseen colors. For this purpose, we use a PPO agent. Evaluating with the Goody obstacle discrimination measure, we can see almost all of them learned to solve the training context, and we compare, in this case, different methods, such as non-contextual, an agent that uses self-attention, the DARL agent, an agent that uses concatenation, which is technically the call agent, and our new agent that uses this contextual attention module that I presented before. So all of these agents are actually successful in solving the training task, more or less. However, when they are presented with a new set of unseen contexts, with seen colors, we can observe a significant performance degradation, while the agent that has the contextual attention module being performing slightly better than the others in greedy obstacle discrimination. And finally, when presented with unseen colors, we can see that all of the agents actually fail to have a meaningful discrimination between the contexts, which might result in from the representation, generalization issues, because the representation cannot generalize to new color due to the limited number of colors used for training. So in summary, in this talk, we had a look at different methods that deal with contextual reinforcement learning, and we also talked about how knowing the context variable can be helpful and how can we use unsupervised learning approaches to learn context variables, and further how we can incorporate these as conditional vectors in policies and learn conditional policies. And finally, we showed that using this framework, we can improve generalization of agents in the contextual reinforcement learning setting. And in the end, we discussed how learning causal variables is important and how non-causal agents fail to generalize to new contexts. And we talked about how we can build kind of mechanisms into agents that can simulate interventions and improve the generalization performance onto a new and unseen context.